Hi. Hi, my name is Gargi, and I'm going to be talking about how printing floating point numbers is surprisingly hard. Um, so you might have an experience with this, like you have a Python REPL and you write 0.1 in the REPL and you get 0.1 as the output, and then you write 0.2 in the REPL and you get 0.2 as the output. Then you add 0.1 and 0.2 in the REPL and you get 0.3, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 4 as the output, which is surprising, right? Because the answer should be 0.3, like it's 2020, why are computers still not working? And you might think the compiler or the interpreter is at fault here, but more often than not, it's the printing algorithm that's the problem. So what is that? Humans love decimal, so if you have 0.25, you can represent it as 25 into 10 raised to the power minus 2 in decimal. And computers love binary, so if you have 0.25, you can represent it as 1 into 2 raised to the power minus 2, and you have an exact binary representation. And decimals to binary is simple for integers because you have a limited range. But if you have, let's say 0.3, and according to IEEE 754 floating point standards, you have a sign bit, and then you have some bits reserved for the exponent and some for the mantissa, and you have a representation for 0.3 in that, and if you convert it back to decimal from the binary representation, you get 0.3, 0, 0, 0, 488, 28125, which is because decimal to binary is one-way compatibility for floating point numbers. So all binary numbers have a corresponding decimal representation, but all decimal numbers do not have a corresponding binary representation. And one thing that we come across a lot when we talk about algorithms for printing floating point numbers is the idea and the concept of correctness. So let's say you have a number v that maps to 0.1, 0, 0, 0, 0, 0, 0, 0, 0, 5, but when you want to print it, what is the correct number to print? So there's an entire range in the number on the number line that will map to v, and in that entire range, what we want to print is the shortest number, which will be the correct answer for printing this floating point number. So the first algorithm to come around for printing floating point number was in 1990 called Dragon 4. So in the early 1970s, systems produced incorrect decimal values of binary numbers, and they didn't provide a guaranteed bound on how wrong they might be. And in around 1980, the IEEE 754 floating point standard came around, but people would more or less pass a working code for reading or writing floating point numbers, and they didn't write too much about correctness because the idea was that floating point is like inherently inaccurate anyway. So to rectify that, Guy and Steele wrote this paper on printing floating point numbers. So, and they put across like 4 criteria to say like how do you print the correct floating point number for, how do you print the correct representation of the floating point number? So the first was information preservation, or you can also call it round tripability. So the idea is that whatever you write and read back should be the same decimal, should be the same number. Second is minimum length. So minimum length is whatever in the interval you get the shortest number possible. Correctly rounded meant even rounded, and left to right generation, when you were generating the correct floating point number, you were starting to generate the decimal the numbers left to right. So the idea in Dragon 4 is that for a number b0, you have a range which goes from value, and margin is the difference between the next number on the is the difference between the next and the previous number on the floating point. The margin is the difference between the next number and the previous number and the number on the number line. So what the number that we want lies somewhere between value minus margin by 2 and value plus margin by 2, and we will sweep across this interval and find the shortest number, and that's the number that we want. So this algorithm is 100% correct, but it's relatively slow because it uses arbitrary precision arithmetic. So it uses big integers to generate the numbers. The next algorithm in this realm came around in 2010s, and it's called CORRECTNESS. This is like one of the most widely used algorithms. So like JavaScript engine uses it, the JavaScript engine uses it, OCaml uses it. Python has like different standards for what makes a good printing floating point numbers, where Python decided to focus on simplicity of the algorithm. So CORRECTNESS has again a similar idea where it will find where you have v, and then you have the previous number that is v minus on the floating point, and v plus, which is the next number on the number line, and you have m plus and m minus, which is the range in which all the numbers round up to v. And what we do in between this range is that we do a narrow approximation. So if you imagine like it's a brush sweeping through this number line, we have a relatively bigger brush. So to do bigger approximations and faster approximations, and then you have a wider approximation that's outside this range of a and b. But what happens is that there's an uncovered interval, and if the narrow approximation and wide approximation matches, then we found out the number in this range that's the shortest number. But if the shortest number lies in this uncovered interval, then we cannot guarantee that we found the correct number, and we will fall back to Dragon 4. So this is 12.5 times faster than Dragon 4 because it does not use arbitrary integer arithmetic, it uses machine integers, and it's correct for 99.5% of the times, and the rest of the 0.5% of the time it uses Dragon 4 as a fallback. So it's relatively complex algorithm, and doesn't really satisfy the simplicity criteria that Python has. So Python uses different algorithm, and the newest algorithm in the land of printing floating point numbers is called RU. So let's say which came around in 2018. So let's say if we have a number that we want to print, and the number is 0.30004882.815, and again we have a previous number on the number line and a next number on the number line, and the 4 criteria that we had from Dragon 4 are still being followed. All the algorithms follow these 4 criteria, where you have information preservation, you have the minimum length, you're correctly rounding, and you have a left to right generation. So how it works is you keep cutting off digits until you get to a point where one of the numbers out of these looks like the upper bound, and for the lower bound, the criteria is that if you have non-zero numbers on the lower bound, you round them up, and on the upper bound, you round them down, and you keep cutting off as many digits as possible, and the algorithm decides how many digits are correct to cut off, and it uses only integer operations, and like it's almost 3 times faster than Kershaw. So one of the challenges with all the floating point printing algorithms is that there are two problems here. There's an input problem where, like, what is the number that you're reading to print, and the other problem is the output problem, which is like, what is the number that you're printing. So all the algorithms assume that the input problem is already solved, and that what they are solving is the printing problem. So if you now do go to like almost all the languages, when you actually print 0.1 plus 0.2, you will get 0.3, because the printing algorithms are not sophisticated enough to do this correctly. And yeah, that's it for me. Thank you so much. Bye.